go ahead and get started. I'm excited about today's lecture because today you are going to become members of the I Understand Newton's Third Law Club, and it's not a big club. It's fairly exclusive. So we're going to start. Homework is for Wednesday because of the holiday, 7, 8, and 9, all about Newton's Third Law, in Chapter 5. Let's start by turning in some homework. Which of these would you rather not turn in? Okay, last call. Okay, number 13 is off the island. Heads will turn in 11. It is tails. Number 16, people. Number 16.
Yeah, I think so.
Okay, people, while you're turning that in, let's see if you understand Newton's second law. There's a question up there on the board. Use your clicker to respond. You should be able to do it in your head. It's pretty easy. Okay. Again, it's a very easy question. Should be able to do it in your head. If you haven't voted, please get your clicker points. Last call. Okay, we don't quite understand Newton's second law yet. Let's see if we can fix that a little bit. All of these force problems start with a free body diagram. That dot represents the wagon and the child. And we're told that wagon and child has a mass of 30 kilograms. Now the first force we put on any free body diagram is the gravitational force, Earth on the wagon and child. And how big is that going to be? Remember last day we found it was equal to the mass times this gravitational field strength, which on the planet Earth is 9.8, let's call it 10, newtons for each kilogram. So I would take the 30 kilograms, I'd multiply it by 10, 9.8, let's call it 10, newtons for each kilogram. That's how hard the Earth pulls on each kilogram. And I end up with 300 newtons. I then asked, I'm following the recipe, I asked, are there any magnets? No, not in this problem. So what touches the wagon and the child? Well, there's the floor and it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Now I'm told that there's a friction force by the floor on the wagon and the child, and that it's 40 newtons. The only other thing touching this wagon and the child is you, and you're pushing with a normal force. And you're told that the result of your push is an acceleration of 3 meters per second every second. Now, once I've drawn a free body diagram, I get to use Newton's second law twice. Once in the y direction. Oh, that was from the last class. Okay. In the y direction, we have F net in the y direction is equal to MAY, but there is no AY. A is to the right. It's not in the y direction, and so that means my diagram in the y direction has to scream balance. So this has to be 300 newtons. In the x direction, I have F net in the x direction is equal to MAX. That's what gives me the scream. This diagram has to scream to the right because it's causing that acceleration to the right. How loud is the scream is given by this formula right here. I've got to take a 30 kilogram object and accelerate it 3 meters per second squared to the right. I need a scream of 90 newtons to the right. Now folks, that is not your push. That is the net force. That's the extra force required. I need to have 90 more newtons to the right than I got to the left. If I've got 40 to the left, I got to have 90 more than that to the right. The answer here is 130 newtons. Okay? Or D. If you didn't get that, you need to slap yourself right now. Right now. I'll wait. Okay. Now we're going to practice using Newton's second law from now till the next exam. For the rest of the day, I'd like to talk about Newton's third law. And to understand Newton's third law, we need to have a deep understanding of what we mean by a force. What is a force? Well, let's go to the dictionary. Webster says it's power of energy, strength, the force of a gale. Power exerted on any resisting person or thing. What, does that look useful? Now, that's a bunch of fancy words strung together in a meaningless way. Okay? Maybe something more spiritual. Press the force. Sorry, Yoda, that's not it. In physics, we look for operational definitions. And an operational definition is a recipe that we follow in order to create the thing we're defining or to measure the thing we are defining. In this case, we would like to get a number for the thing that we are defining. Now, we know that a force at a gut level is a push or a pull. So if I'm measuring a pull, what I might do, I come over here to Barrett and we shake hands and we pull. Okay? Now if I want to quantify, if I want to measure that pull, what I would do is I would take this spring scale that measures in newtons, and what I would do is while I'm pulling, I would slide this in there and I'd pull the same way. And that reading would be the magnitude of that pull. Now, Barrett and I are pulling on each other. If I want to measure how hard I'm pulling, I put the spring scale in this way. What if I were to turn it around? What if I were to turn it around and put it in? And now we measure how hard Barrett's pulling. What we find is we get the same number. That's Newton's third law. Now if we've got a push, we can't use a spring scale, we've got to use a bathroom scale. If I'm pushing on this wall with a normal force, and I want to define that force by measuring it, what I would do is I'd push, and then really quick, I keep pushing the same way, slide that in there. And I'm pushing with 17 pounds, okay? Now, if I wanted to measure instead how hard the wall is pushing back on me, instead of sliding that in this way to measure my push, I'd slide it in this way. And if the walls had eyes like they did during the Cheney administration, it would read the same thing. Exactly the same thing. Okay? That's Newton's third law. That's Newton's third law. Now, a force is a vector. It has magnitude and direction. And we just defined the magnitude. The direction is just use your gut. When Barrett and I are pulling on each other, my gut tells me I'm pulling him this way. His gut tells him he's pulling me that way. Opposite each other. So by Newton's third law, these forces that we exert on each other are equal in magnitude, opposite in direction. Now, how many of you have seen the movie Groundhog Day with Bill Murray? One of the classics, one of the best movies ever. Now those of you that haven't seen it, that's what you got to do this weekend. You got to go watch the movie. In it, Bill Murray is stuck in Groundhog's Day. He's got to live it over and over and over again until he gets it right. And every day is the same. Every day these same things happen. And so let's suppose that I'm stuck in Groundhog's Day. And one day I notice that at 4 o'clock in the afternoon there's a collision between a little red car and a great big truck. No one gets hurt. It's fine. But the geek in me is a little bit curious. And so the following day, which is the same day, which is Groundhog's Day, I'm standing at the side of the road right at 4 o'clock waiting for these two to collide. And right before they collide, I slide this bathroom scale between their bumpers, and the driver of the red car, oh my, that's a big number. Now the next day, which is the same day, which is Groundhog's Day, I'm back again at 4 o'clock, and this time I've got the bathroom scale this way. And right before they collide, I slide it in so that the trucker can see the number. Oh my, that's a big number. Who sees the bigger number? The little red car or the big truck? Newton says the same. But he's dead. Do we really believe it? I mean, the truck was loaded down with gold. That was why I was interested. It was speeding because it was late. Is the force really going to be equal and opposite? Do you really believe that? Let's find out. I have here a way of measuring force. I have here these force probes, and what they measure is just how hard you push on them. I'm going to zero them out. And this one measures how hard I push on it in red. And this one measures how hard I push on it in what's supposed to be blue, but is whatever. Okay? Now what I'm going to do here, I'm going to zero them out again. And I'm going to give myself some more time because I'm not that fast. Okay? And I'm going to collect and okay. Now, let's blow this up. Now, that's messy. There's a lot of ringing going on. It's a complicated force. But if you look, whatever happens to one car happens to the other one exactly the opposite direction. Whatever happens to one car happens to the other. It's just a mirror image. Now I got to tell you, In 1998, I was team teaching this class with Jeff Adams. We received those force probes on the morning that we were supposed to teach about third law. We did not have time to play with them. And so we just took a gamble. We said, hey, why don't we try it during lecture? So the first time we ever used these force probes was during a lecture like this. The cards collided, and Jeff and I just stood there. Oh, it's true. I mean, we taught it for years, but we didn't believe it. But it's true. And then the rest of the lecture was over, because after that we did it again and again. We parked this one and we rammed this one really fast. We put a lot of weight on this one and we rammed it back over. We could never get them to be different. They were always exactly the same. It's the most beautiful thing in the world. Now, in case the technology didn't work, I was going to say, there you go. Nice. Now, let's state Newton's third law. For every, finish. For every action, there's an equal and opposite reaction. For every action, there's an equal and opposite reaction. Excuse me, sir, what's your name? Jake. Jake has not been paying attention. That just steams me. So I come over and, pow! Smack him right in the jaw. Action. Now, Jake has never been hit by a professor, not during lecture before, and so he's upset. He's waiting for me in the hall after class. And as I walk out there, pow! Reaction. Is that the action-reaction that Newton was talking about? No. At the very instant that my fist hits Jake's jaw, what? His jaw hits my fist. Which of those is the bigger force? They're equal. You just saw they were equal. What that means is at the very instant that I hit Jake, we're even. This has terrible consequences for parenting. Now, when my kids were younger, the youngest came running into the kitchen, just tears streaming down his face. Josh hit me! Josh hit me! His older brother came running right in behind him. You hit me back just as hard. I did not! I did not! Yes, you did. Third law. What can I do as a parent? I believe third law. Now, I don't like that language, action, reaction. It suggests that one of the forces is more fundamental than the other, more important than the other. I prefer this language. If a red object pushes on a blue object, the blue object always pushes back with a force that's equal in strength and opposite in direction. What that means is that throughout the universe, there is no such thing as a single force. All forces are married. Marriage is what brings us together. No, but seriously, all forces come in sets of two. Okay? And this is how you recognize them. If I have a red object colliding with a blue object, the third law companion forces will be recognized this way. First of all, they will be the same flavor because they're part of the same interaction. If one is a normal force, the other one has to be a normal force. If one is a tension force, the other one has to be a tension force. If one is a gravitational force, this one has to be a gravitational force. Second, and I cannot emphasize this enough, they will never, ever, ever appear on the same free body diagram. One of them acts on the red object, one of them acts on the blue object. One of those forces was hurting Jake's jaw, the other force was breaking my fist. Okay, they never act on the same object. The third thing, these indices, blue on red, red on blue, they will always be the same, reversed. You can almost hear them get up and pirouette and come back down. Okay, listen for the sing-song. The normal by the blue on the red, the normal by the blue, red on the blue. It's late in the day. Now, we are ready for a concrete example. That's what I'm going to give you. A concrete example. First of all, let me get this out of the way. Okay, let's do a concrete example. See if your neighbor's on the bus, people. Do a buddy check. Okay. We're going to do a concrete example. We have a concrete launch pad down in Florida, and on that is a rocket ship. And that rocket ship is blasting off 10, 9, 8, 7, 6, 5, 4, 3. Looks like that. Now, all forces are an interaction between two things. Things you can taste, smell, touch. Okay? They push on each other or they pull on each other. I would ask you, what thing is pushing on the rocket? What thing is pushing on the rocket? Talk to your neighbor. What thing is pushing on the rocket? My second question is this a contact force or a non-contact force? Now, we're going to actually do this. Yeah, that's what I'm talking about. Okay. Rocket Man. Okay. I need a countdown. 5, 4, 3, 2, 1. This demo has not always gone well. 23 years ago, I was lecturing over in Reed Hall 108. It had a stage like Reed 105, and I was just rocketing across that stage, heading for a brick wall. I immediately turned around to give air brakes, but I forgot to stop spraying, and I took out the front row. Another time, I went to an elementary school, like that. And we have two of these. One that fires out this way, and another one that fires out perpendicular. And I forgot which one I had. Hey kids! Pow! And it hit me right in the forehead. I landed on the ground. The third graders thought it was great fun. Now, let's talk about that. When I was over here, I was able to push against that wall. What was I pushing against when I was over here? The air. Okay. Now, I'm going to suggest an experiment. Suppose we start in the middle of the room, away from that wall. And then we're going to close these doors and suck all the air out. Take a deep breath. We close the doors, we suck all the air out. And then I sit here and I go, psh. Do I go anywhere? Yes. Come on, people, you saw Apollo 13, right? They're in outer space trying to get home. right? Okay, if you didn't see that movie, you saw Wall-E. And he had the fire extinguisher and he was just kind of going around in space. Folks, we don't need the wall. We don't need the air. We don't need the concrete launch pad. That only serves to keep the rocket out of the mud. What is pushing on what? Every force is an interaction between two things. In this case, this cylinder is pushing on what? The compressed CO2, the fuel. And if it's taking that fuel and throwing it, pushing it that way, by third law, it's pushing on the canister this way. And that's how rockets work. That's how rockets work. Now I'm embarrassed to admit that I did not always appreciate this. When I was 14, my neighbor, his name was Paul Jonke, and I were geeks. And we did experiments. And a lot of those experiments involved rockets. And we had these little rockets that had solid pellets that were the fuel. And it kind of looked like that without the man. And one day, we were making a rocket, and I wanted to make it look like a spaceship. So I went and borrowed, by which I mean stole, a pie plate from my mother, and we attached it. And then I said to Paul, Paul, it's a crying shame that NASA can't bring the launch pad with it. I mean, they get that really good boost at the beginning, but then not so much. What if we were to bring our launch pad with us? So I went and borrowed, by which I mean stole, another pipe plan, and we bolted them together. Now what does that look like to you? Yeah, that's a bomb. That's exactly how it worked. That's exactly how it worked. And that's how I learned. Okay. Now, let's look at this problem. This is a problem that they give you to see whether you're worthy for business school. Okay? You're holding a bag of gold. You're on a frozen lake. And it turns out that that lake has a surface which is perfectly frictionless, and you're in the middle. What do? Throw the money. Take the money and throw it this way. You'll go the other way. You just got X'd out of business school. If you let go of the money, you're not worthy. Okay, so let's see how you could get off of this pond of ice without letting go of the money. So I could just blow. No, that's not going to work. Turns out, if you're going to business school, you're going to have to take off your clothes and throw them. And that's how we know that you're ready for business school. If you will strip naked before letting go of that gold, you should go to business school. Okay? Now, let's look at the poor Gary problem. Gary, after studying Newton's third law, is finally convinced that it's true. Unfortunately, he's convinced himself while sitting in a classroom with a single closed door. He wants to go out, but he says, if I push on the door to go out, Newton's third law tells me the door is going to push back just as hard with an equal force. That force is going to cancel the force I push with. Even if I push as hard as I can, that door is going to push back just as hard. Oh no, I'm stuck in this room. Why did I ever study physics? You feel like that sometimes? Yeah. Now clearly there's a flaw in Gary's reasoning. Because he can push on that door, and that door is going to open. Find the flaw in Gary's reasoning. Talk to your neighbor, please. Okay, brave soul, raise your hand. What's the flaw? Ray, where are you, brave soul? Yes, sir.
You're not in a frictionless environment.
Ah, the friction on the floor. I am so embarrassed that I forgot to tell you this. It turns out that the night before, the janitors came in and they were using a new kind of wax. It's called frictionless, totally frictionless. And I mean, it's just a fluke. And he pushes, the door opens and he scoots, but the door does open. Brave soul, yes.
Is it the hinges on the edge of the door?
The hinges on the door. What's up?
They kind of focus and it's not like a wall. It's not just it kind of concentrates where that resistance is.
Okay, let's suppose there weren't any hinges, and it's just kind of leaning there. I push, it falls down, I go out. Brave soul, where are you? Yes.
Does equal and opposite reaction include direction of the reaction?
Yes, and so one is a force that way on the door, and one is the force this way on the Gary. So they're equal and opposite. Yes, sir.
He has to have a greater mass than the door.
And that's another coincidence you can scarcely believe. It turns out, I mean, who would have guessed? Gary and the door have exactly the same mass. I didn't see that coming, but it's true. Equal and opposite are always relevant, so I'm going to say no to that one.
The door opens, you just might not necessarily get out.
The door will open, but he might not get out. But why does the door open? Why don't these cancel each other?
There's an extra force, so in order for it to cancel out, it has to be the same type of force. to cancel out.
Okay, so they are the same kind of forces. I'm not sure I understand.
The force didn't cancel because the forces are not exerted on the same object.
Oh, would you please say that again? That is so wonderful.
I forgot what I said.
I will remember what you said. You said they cannot cancel because they do not act on the same object. That's it entirely, okay? If I draw a free body diagram for the door, there's lots of forces on that diagram. There's the weight down on the door. There's the hinges pushing up the door. And there's this force, a push by Gary on the door. Now if I draw a free body diagram for the Gary, again there's a weight of Gary, there's the normal by the floor on Gary. If we didn't wax it with the frictionless wax, there would be a friction force by the floor on Gary. And then there's this force, the normal by the door on the Gary. And these two forces by third law are always equal and opposite. If this one gets bigger, so does this one. But they cannot cancel because they do not act on the same object. When I'm interested in the motion of the door, whether it will open or not, I use F net equals MA for the door. Now, F net is just all the forces on the door. This one can't cancel that one because it doesn't get to play in this equation. Likewise, when I'm looking at the motion of Gary, whether he slides across the room or not, I use F net equals MA for the Gary. And that F net is all the forces on this diagram. And again, that force can't cancel this one because it's not in the equation. The most famous version of this question is the old horse and cart problem in New York Central Square, Central Park. If you've got a horse pulling a carriage through Central Park, if the carriage is always pulling back on the horse just as hard as the horse is pulling forward on the carriage, how do they get anywhere? And the answer is only one of those forces is speeding up the cart. The other one is slowing down the horse. Okay, see if your neighbor understands that. Okay. How many of you want to go to medical school, be doctors? You got to take the MCAT. And on that MCAT, there's this famous bug problem that everybody misses. A bug splats on the windshield of a car moving at 100 miles an hour. Which feels the greater force, the bug or the car? Newton says they're the same. But everyone misses this problem because they're really answering a different problem. Who had the worst day? Yeah. Now that force is the same, but that force is not enough to affect the car at all. Doesn't slow it down a bit. But that force is enough to ruin the bug's whole day. Okay? Now another example of that is if I drop this book, it goes rushing down. Now Newton says that if the earth is pulling down with a 1 pound gravitational force, that the book is pulling back up on the earth. But when I let go, they don't rush to meet each other, do they? The forces are the same, but the effects, the acceleration, depend on the mass. Now in this case, the force is just enough to make this book accelerate at 9.8, let's call it 10 meters per second down. You take that same force and apply it to the earth, negligible. Negligible. Okay? Now, in your tutorial homework, you have this problem. You have 4 identical links of a chain, and it's being suspended by a rope from the ceiling. You're asked to draw free body diagrams for each of those links, 1, 2, 3, and 4. Now, because they're identical, they would all have the same mass, and hence the same weight. For the sake of concreteness, let's give that a number. Let's call that weight 3 newtons. Okay, just made that number up. 3 newtons. Now when you're drawing free body diagrams of things that interact, I would strongly suggest that you always draw the free body diagram of the simplest object first. The object that's touching the fewest other things. Which object should I draw the free body diagram for? 4. Okay. So, I've got the weight force. There's no magnets in this problem. What touches 4? 3. Does it push or does it pull? Yeah, now here we've got a kind of a gray area. If I look at what's actually happening, the one link is pulling up on the other link, and I would call that a tension force. But if you look really, really closely at what's happening at the surface between those 2 links, they're pushing on each other. And so whether you call that a tension force looking from afar, or whether you call that a normal force looking up really close, I don't care. You'll get full credit either way. I'm calling it a tension force, and I'm here to tell you that if this is 3 newtons, that's got to be 3 newtons. They are equal and opposite by what law?
Second.
Yeah, if you said third law, you got to slap yourself silly until you get over it. Let's look. These cannot be related by the third law. They're not the same flavor force. They're on the same dot. They don't have the same indices reversed. These are equal and opposite by second law. And when you invoke the second law, you have to qualify your statement. These are equal and opposite by second law with 0 acceleration. If I've got 0 acceleration for this link, my diagram has to scream balance. I only have 1 force up, 1 force down. They got to balance by second law with 0 acceleration. Now I use third law. 3 cannot pull up on 4 without 4 pulling back down on 3 just as hard. If this one's 3 newtons, that one's 3 newtons. And I put a tick mark to indicate that they are part of a marriage, part of a third law companionship. Okay? Now the only other thing touching 3 is 2, and it pulls up. Now by second law with 0 acceleration, if this is 3 and that's 3, that's got to be 6. My diagram has to scream balance. Now, if 2 pulls up on 3, 3 has to pull down on 2 by third law. And I use 2 tick marks to indicate that they're part of a match set. I then asked what else pulls on 2. Well, 1 does. It pulls up. If this force is 6 newtons, and this one is 3 newtons, by Newton's second law with 0 acceleration, that must be 9 newtons. Again, I use the third law. 1 cannot pull up on 2 without 2 pulling back down on 1. And I put 3 tick marks there. And finally, I have the rope pulling up. If this pole is 9 newtons and this one is 3 newtons, that's got to be 12 newtons, which just happens to be the weight of all 4 links together. Check that your neighbor got this homework problem correct. Okay? Let's look at this example. This example is very similar to a lot of the problems in your tutorial homework. We have a single can, a pop can, sitting on a table. If I draw a free-body diagram for that, I have the weight down, earth on the can. There's no magnets. We're getting to them. Just be patient. So what touches the can? Well, the table. Does it push or does it pull? It pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force, but I don't need one if that's a level table. Now, those 2 forces are equal and opposite by what law? By second law. Second law with 0 acceleration. Now, in your tutorial homework, on the first page and part of the second page, Lillian McDermott is trying her darndest to get you to see that those are not third law companions. And in this example, we can show that's true by putting that can and that table in an elevator with acceleration up. Now, before we go further, is that elevator moving up or moving down? Is it going up to the 10th floor or going down to the lobby?
Going nowhere.
Do we know? If it's going up, what is it doing? Speeding up. If it's going down, what is it doing? Slowing down. And both of those feel exactly the same. If you don't have windows in your elevator and you don't have any glowing buttons, you don't know which one you're doing. Okay? Now, this diagram has to scream that acceleration. So what has to change in my diagram? Does this one change? No. The earth is pulling on that can regardless. It doesn't care what the can is doing today. The only way you can change that force, people, believe me, is diet or exercise. If there were something else, I would have done it. Okay? Diet or exercise. So in order to make this diagram scream up, the normal force has to get greater. And now we see that these could not be the equal and opposite third law companions because they're not equal. Now, what is the companion force to that normal force? Well, what flavor would it be? Normal. And instead of table on the can, it would be can on the table, like that. What free body diagram would I find that on?
The table.
Yes, this is a force by the can on the table. And that means it's on the free body diagram of the table. And I would put 1 tick mark on each to show that they're part of the same interaction. Now what about this gravitational force? Does it have a third law companion?
Yeah.
All forces have third law companions. This is the earth pulling on the can. If I look at a free body diagram for the Earth, there will be a bazillion different forces, but one of them will be a gravitational force of the can pulling up on the Earth. And I would put 2 tick marks there. Now, if you're ever comparing forces on the same free body diagram, on the same dot, you use Newton's second law, and you qualify it. I would say that normal force is bigger than the weight by Newton's second law with acceleration up. But whenever you invoke Newton's third law, you just say they're equal by third law, full stop. You don't care whether it's accelerating, not accelerating, Tuesday, Friday. If they're equal by third law, they are always equal by third law. And you can recognize they're equal if they're the same flavor with the same indices reversed. Now, 23 years ago, I came to this campus and joined the faculty here. I have a different sort of a job than most of the professors here. I teach a lot. I don't do as much research. I write textbooks. Now, that first year, a graduate student came and said, a member of my thesis committee has bailed out, he left town, and I'm supposed to have my graduate PhD thesis defense on Friday. Could you fill in? I said, sure. So I show up, and at a graduate level PhD thesis defense in our department, 5 professors from physics and 1 professor from another department listen to a presentation for 45 minutes and then grill the student for as long as they want. They can ask any question about physics. So this student, we'll call him Bill, that's not his real name. This student was brilliant, and he gave a wonderful presentation. He just had everything just nailed down. And then we started asking him questions. And after 2 hours, it started to become apparent to the others in the room that this new guy, Greg Francis, had not yet asked a single question. And finally, it became so obvious that the chair of the committee said, Professor Francis, would you like to ask a question? And I said, sure. Bill, you got a can on the table there. Would you draw me a free body diagram for it? And the other professors were kind of concerned that they had hired the wrong guy. And Bill was just disgusted. This is his thesis defense. He just goes to the board with a look of scorn on his face, and he says, well, there's weight down and there's a normal force up. I said, okay, Bill. Newton says for every force there's an equal and opposite reaction force. What's the third law companion force for that normal force? Bill went to the board and he said, well, a force that's equal and opposite to that is that. And suddenly the other professors in the room knew where I was going. And I said, well, Bill, why don't you just lean over and push down on that can? What happens to your free body diagram? He says, well, I have a push, and that gets bigger. Wait a minute, Bill. You said that normal force was a companion force to the weight. They're not equal anymore. He looked all concerned. He got really, really nervous. And he said, but that force is equal and opposite to those two. I said, oh. So every force there's an equal and opposite group of forces. And then he really got nervous. And I said, Bill. I said, Bill, don't push down on the can anymore. Let's just put the whole thing in an elevator with acceleration up. What does the diagram look like now? He said, it looks like that. There's only 2 forces, and they're not equal and opposite. And he looked concerned, he looked worried, and then suddenly he burst out into a smile. And he said, oh, Newton's third law doesn't apply when something's accelerating. And the room turned to ice. I leaned forward and I said, Bill, your dog will die. Your children will move away from home. But Newton's third law will always apply every single time. And that's my message for you. Okay? Have a good weekend, people. We'll see you on Wednesday.